Welcome and introduction. Welcome to the channel. Please consider subscribing. I produce videos daily, covering a wide variety of cloud topics, focusing on networking. Also, hit the bell icon to get notified of new videos. Today, we're going to demystify one of the most elegant concepts in cryptography, the Diffie Hellman key exchange. Don't worry if you're not a math wizard. I'll explain this using simple analogies that anyone can understand. Imagine you and your friend want to share a secret password, but you're in different countries and can only communicate through postcards that everyone can read. How do you create a shared secret without anyone else knowing what it is? That's exactly the problem Diffie Hellman solves. This algorithm, invented in 1976 by Whitfield Diffie and Martin Hellman, revolutionized secure communication and is still the foundation of much of our internet security today. Every time you see that padlock icon in your browser, there's a good chance Diffie Hellman is working behind the scenes to keep your data safe. The color mixing analogy. Let me start with my favorite analogy for understanding Diffie Hellman: mixing paint colors. This is something we have all done as kids, and it perfectly captures the essence of how this algorithm works. Think about mixing paints. If I give you a bucket of blue paint and a bucket of yellow paint, you can easily mix them to get green. But here's the crucial part. If I give you a bucket of green paint, can you separate it back into the exact amounts of blue and yellow that were used? No, you can't. This one-way property is what makes Diffie Hellman secure. In our analogy, Alice and Bob want to create a shared secret color. They start by agreeing on a common color that everyone can know. For example, yellow. This is like agreeing on public parameters in the actual algorithm. Then, each person picks their own secret color that they never share with anyone. Alice might pick red as her secret, and Bob might pick blue as his secret. Now watch the magic happen. Alice mixes her secret red with the public yellow to get orange. Bob mixes his secret blue with the public yellow to get green. They then exchange these mixed colors publicly. Anyone can see that Alice sent orange and Bob sent green. Here's where it gets brilliant. Alice takes Bob's green and adds her secret red to it. Bob takes Alice's orange and adds his secret blue to it. Both end up with the same final color, a brownish mixture. But someone watching the exchange only sees yellow, orange, and green. They can't figure out the final secret color without knowing either red or blue. The mathematical foundation. Now that you understand the concept through colors, let us peek under the hood at the actual mathematics. Don't worry, I will keep it simple and relate everything back to our color analogy. In the real Diffie Hellman algorithm, instead of mixing colors, we use something called modular arithmetic. If you have ever looked at a clock, you already understand modular arithmetic. When it is 10 o'clock and you add 3 hours, you get 1 o'clock, not 13 o'clock. That is because clocks work in modulo 12. After 12, we wrap back around to 1. The algorithm uses 3 public values that everyone can know. First, there's a prime number p. Think of this as the size of our clock. Instead of 12 hours, we might use a huge prime number with hundreds of digits. Second, there's a generator g. This is like our starting position on the clock. These two numbers together are like the public yellow paint in our analogy. Each person then picks a secret number, their private key. This is like picking your secret color. The clever bit is that we use exponentiation with modular arithmetic. If my secret number is a, I calculate g to the power of a modulo p. This is like mixing my secret color with the public yellow. The mathematical process works because of a fundamental property of exponents. G to the power of a, all raised to the power of b, is equal to g to the power of b, all raised to the power of a. Both of these are equal to g to the power of a multiplied by b. This means that when Alice and Bob exchange their computed values and then apply their private secrets again, they both arrive at g to the power of a multiplied by b modulo p. This effectively becomes the identical shared secret. However, an observer cannot easily determine the individual values of a or b, simply by seeing g to the power of a modulo p or g to the power of b modulo p. This computational challenge is known as the discrete logarithm problem, and it is widely believed to be extremely difficult to solve, especially when dealing with very large numbers. Step-by-step process. Let me walk you through the Diffie Hellman process step by step, using actual numbers so you can see how it works in practice. I will use small numbers to keep it simple, but remember that real implementations use numbers with hundreds or thousands of digits. Step 1. Alice and Bob agree on public parameters. Let's say they choose p equals 23, a prime number, and g equals 5, a generator. These numbers are public. Everyone can know them. Think of this as choosing the public yellow paint that both will use as a base. Step 2. Each person generates their private key. Alice randomly picks a equals 6 as her secret. Bob randomly picks b equals 15 as his secret. These numbers are never shared with anyone. They are like the secret colors each person chose. Step 3. They create their public keys. Alice calculates a equals 5 to the power of 6 modulo 23 equals 8. Bob calculates b equals 5 to the power of 15 modulo 23 equals 19. Notice how even with small numbers, the intermediate calculations grow quickly. Alice sends 8 to Bob, and Bob sends 19 to Alice. These are the mixed colors that everyone can see. Step 4. They compute the shared secret. Alice takes Bob's public key and raises it to her private key. 19 to the power of 6 modulo 23 equals 2. Bob takes Alice's public key and raises it to his private key. 8 to the power of 15 modulo 23 equals 2. They both get 2. This is their shared secret that no one else can calculate without knowing either a equals 6 or b equals 15. An eavesdropper sees p equals 23, g equals 5, a equals 8, and b equals 19, but to find the shared secret, they would need to solve for either a or b, which requires solving the discrete logarithm problem. With our small numbers, this is easy, but with huge prime numbers, it becomes computationally infeasible. Real-world applications. Now that you understand how Diffie Hellman works, let's explore where you encounter it in your daily digital life. The applications are everywhere, and you have probably used Diffie Hellman thousands of times without knowing it. https://tls. Every time you see the padlock icon in your browser or visit a website starting with https://, there is a good chance Diffie Hellman is involved. When your browser connects to a secure website, it often uses Diffie Hellman to establish a shared encryption key. This happens in milliseconds, creating a secure tunnel for your credit card numbers, passwords, and personal information. Virtual private networks, or VPNs. When you connect to a VPN to secure your internet connection or access your company's network from home, Diffie Hellman often handles the initial key exchange. It allows your device and the VPN server to agree on encryption keys without ever transmitting them directly. Messaging apps. Popular encrypted messaging apps like WhatsApp, Signal, and iMessage use variations of Diffie Hellman. Signal, for example, uses the extended triple Diffie Hellman protocol, which involves multiple Diffie Hellman exchanges to provide even stronger security guarantees. SSH Secure Shell. If you have ever connected to a remote server using SSH, Diffie Hellman was likely used to establish the initial secure connection. It is part of what allows system administrators and developers to securely manage servers from anywhere in the world. IPsec and network security. Many corporate networks use IPsec for secure communication between offices. The Internet Key Exchange (IKE) protocol, which sets up IPsec connections, relies heavily on Diffie Hellman for its key negotiation. The beauty of Diffie Hellman is that it solves a fundamental problem. How do two parties agree on a secret key over an insecure channel? This capability is the foundation of modern secure communication. Security considerations. While Diffie Hellman is elegant and powerful, it is important to understand its limitations and the security considerations for real-world implementations. No cryptographic algorithm is perfect, and knowing the potential weaknesses helps us use it more effectively. Man-in-the-middle attacks. The classic Diffie Hellman algorithm does not authenticate the parties involved. Imagine if someone intercepted the color exchange in our analogy. They could perform separate exchanges with both Alice and Bob, making each think they are talking to the other. This is why real implementations combine Diffie Hellman with digital signatures or certificates to verify identities. The security of Diffie Hellman depends heavily on choosing the right parameters. The prime number p needs to be large enough. Current recommendations suggest at least 2048 bits for short-term security and 3072 bits or more for long-term security. Using weak or poorly chosen parameters can make the system vulnerable to attacks. Small subgroup attacks. If the parameters aren't chosen carefully, attackers might be able to force the shared secret into a small, predictable set of values. This is why cryptographic libraries use carefully vetted parameter sets that have been analyzed by experts. Looking to the future, quantum computers pose a threat to Diffie Hellman. Shor's algorithm, which runs on quantum computers, can efficiently solve the discrete logarithm problem that Diffie Hellman relies on. This is why researchers are developing post-quantum cryptography to prepare for this eventuality. Implementation vulnerabilities. Even with perfect mathematics, poor implementation can introduce vulnerabilities. Side-channel attacks might leak information through timing, power consumption, or electromagnetic emissions. Protecting against these requires careful coding and sometimes hardware-level countermeasures. Despite these considerations, Diffie Hellman remains one of our most important cryptographic tools when used properly. The key is understanding these limitations and implementing appropriate safeguards. Modern variants and improvements. Since its invention in 1976, Diffie Hellman has evolved and spawned numerous variants, each addressing specific security needs or performance requirements. Let's explore some of the most important modern adaptations that keep this classic algorithm relevant in today's digital landscape. Elliptic curve Diffie Hellman, ECDH. This is perhaps the most significant evolution of the original algorithm. Instead of using modular arithmetic with large prime numbers, ECDH uses the mathematics of elliptic curves. The advantage? You can achieve the same level of security with much smaller numbers. A 256-bit elliptic curve key provides roughly the same security as a 3072-bit traditional Diffie Hellman key. This means faster computations and less data to transmit, which is crucial for mobile devices and IoT applications. Ephemeral Diffie Hellman, or DHE/ECDHE. The E stands for ephemeral, meaning temporary. In this variant, new Diffie Hellman parameters are generated for each session. Even if an attacker later compromises a server's long-term private key, they cannot decrypt past communications. This property, called forward secrecy, is now considered essential for secure communications. X25519 and X448. These are specific elliptic curves designed for Diffie Hellman that offer excellent performance and security. X25519, in particular, has become incredibly popular because it is fast, secure, and resistant to many implementation errors that plague other curves. It is used in Signal, WhatsApp, and many modern TLS implementations. Post-quantum variants. With quantum computers on the horizon, researchers have developed new key exchange methods that should remain secure even against quantum attacks. These include lattice-based schemes like New Hope and Kyber, which are based on different mathematical problems that quantum computers can't easily solve. Authenticated Diffie Hellman. Various protocols combine Diffie Hellman with authentication mechanisms. For example, Sigma provides authentication while preserving the perfect forward secrecy properties of ephemeral Diffie Hellman. These variants show how a fundamental idea can be adapted and improved over decades to meet changing security needs. Conclusion and future outlook. As we wrap up our journey through the world of Diffie Hellman key exchange, let's reflect on what we've learned and look toward the future of secure communication. We started with a simple question. How can two people create a shared secret, even when everyone can see their communication? Through the paint mixing analogy, we saw how one-way functions, easy to compute in one direction but hard to reverse, provide the answer. We then dove into the actual mathematics, seeing how modular exponentiation creates this one-way property in practice. The elegance of Diffie Hellman lies in its simplicity. With just a few mathematical operations, it solves a problem that seemed impossible before 1976. This breakthrough laid the foundation for the secure internet we rely on today. Every online purchase, every private message, and every secure connection owes a debt to Diffie and Hellman's insight. Looking forward, Diffie Hellman faces new challenges. Quantum computers threaten to break the discrete logarithm problem it relies on. But the cryptographic community is not standing still. Post-quantum alternatives are being developed and standardized. The core idea of Diffie Hellman, using mathematical one-way functions to establish shared secrets, will likely persist even as the specific mathematics evolve. For developers and security professionals, understanding Diffie Hellman is not just academic, it is practical knowledge that helps in making better security decisions. Whether you are configuring a web server, designing a secure protocol, or just trying to understand how your encrypted messaging app works, the principles we have discussed today apply. Remember, cryptography is a tool, and like any tool, it must be used correctly. Always use well-tested implementations, keep your systems updated, and stay informed about new developments in the field. Thank you for your attendance. Please consider subscribing to the channel.